So welcome to the last talk of this session. The last talk will be by Dr. Ratnadeep Acharya from Harishchandra Research Institute, Prayagraj. And the title of his talk is A Modular Analog of a Problem of Vinogradov.
Thank you. Am I audible? Can you speak a bit loudly? Am I audible? Yes. Okay. Thank you for the introduction, and I'd also like to thank the organizers for giving me the opportunity to speak in front of you. So, as you have seen, the title of my talk is A Modular Analog of a problem of Vinogradov. Okay. So it's a joint work with Sari Rapu, Shatadal Ganguly, and Olivier. Okay. So, thanks to the previous speakers, I don't require to introduce much about holomorphic cast forms. Let F be a cast form, holomorphic cast form of level n and weight k, and we need some technical assumptions on F. First, F is Hecke form, Hecke eigenform. Secondly, F is primitive. And third one is F is non-CM. So such a form, if admits a Fourier expansion, this form where Z is in the upper plane, lambda Fn to be k minus 1 over 2 P of nz. These lambda Fn's are called the normalized nth Fourier coefficients of F, and we are interested in the distribution of the arithmetic function lambda Fn. So it is known that this function is Hecke multiplicative. So it's Hecke multiplicative. So by that we mean that this is a multiplicative function, and moreover, the prime powers and the value at prime powers can be expressed in terms of the values at primes. So therefore, the form can be determined by the values at primes. Say the sequence is determined by the sequence lambda p, where p runs over primes. And so these coefficients are also real. we have made no assumption, nothing about the Neventibus. So it means that we are considering trivial Neventibus. So now the Ramanujan conjecture predicts that, so which is also proved by Deligne, that the values at primes is absolute value is bounded by 2. Okay. So it's natural to write lambda p by this twice cos theta fp, where this angle theta fp lying inside 0 to pi. The Sato-Tet conjecture tells us that this angle theta p, which is, this conjecture is also now a theorem by Clausel, Harris, Barnett-Lamb, and Taylor. So this conjecture tells us that this angle theta fp so these are equidistributed in 0 to pi. That means, so equidistributed with respect to the Sato-Tet measure. So in particular, to mention a consequence of this conjecture is that given any interval I inside -2 to 2, which is of course of positive Lebesgue measure, so this any such interval contains infinitely many values of lambda fp. So that means there exist infinitely many primes p such that lambda fp belongs to this I. Okay. So the question is here, which we want to study, that given such an I, what is the least prime such that the Fourier coefficient lambda fp belongs to that interval. So given such an interval I, what is the size of the least prime p such that lambda fp belongs to I. So this question can be viewed as a modular analog of the problem of Vinogradov, which I didn't mention yet. So let us recall what is the problem of Vinogradov in this context. Is that Vinogradov asked the question is the following question. So what is the size of the least quadratic non-residue modulo some prime p and odd prime? So, and it is known that the residues and quadratic residues are equidistributed. So the question is very natural. And the best known result in this direction is due to Burgess. Prove that so there exists where here least quadratic non-residue. Yes. What? Not distribution. No, we don't require such a jet. So, yes, yeah, sure. No. So there exists. So this is a particular case of interval. I mean, whenever we consider the interval to be -2 to 0. So Burgess' result is that there exists a prime P, or should say, take this to be Q, and there exists a prime P which is less Q to the power 1/4 square root of T plus epsilon, and the absolute implied constant depends on epsilon, such that this is a quadratic non-residue modulo Q. Okay, so let us go back to our question. So an answer to this question was given by Lemke, Olivier, and Turner to prove that for any interval I inside -2 to 2, there exists constant, positive constant A, such that there is a prime. So, well, I made a mistake. There exists a prime P and positive constant which depends on I, such that lambda f p belongs to I with the size is Q to the power 3, where this Q is the, or we should say QF is the arithmetic conductor of F. So one can think of, when the level is fixed, you can consider QF to be K squared, or when the level is fixed, or when the weight is fixed, you can consider it to be N. So our aim is to But I mean, first note that, I mean, in this theorem, this A is not explicit, the constant. And the significance of this result is that that holds for any interval inside -2 to 2. However, this constant is not explicit, and if it can be expressed effectively, then it provides some quite large values of A for almost of all I. So our goal is to find some A as small as possible satisfying these conditions. Satisfying star for some specific intervals. Okay. All right. So before we state our main theorem, I need to mention a hypothesis, HL. So by HL, we mean that the symmetric Lth power of F has an analytic continuation to the whole complex plane C, and moreover, I mean, its value, the value of this L function at the critical line, and is bounded by QF, not QF, sorry, Q sim square F, sim LF to the power some lambda L. Okay. No, so here I mentioned that, so this you can consider K square when N is fixed.
Okay. This is the analytic conductor of symmetric square.
Yes. Analytic conductor?
The analytic conductor of Singh square there at 0. That's a function of the Archimedean parameter.
Yes.
And here the Archimedean parameter is K.
Yes, the Archimedean parameter is K, but I mean,
Yes, so this is basically the analytic conductor.
analytic conductor.
Maybe N squared also. I don't know. I think it's K squared.
K squared N.
Yeah.
So, I mean, I've considered two cases. I mean, when N is fixed or K is fixed. So when N is fixed, we consider K squared, and otherwise consider N or K fixed. Okay. Now, some remark about this hypothesis. First, you shouldn't go there.
And there, what symmetric power you have?
All symmetric L. Very strong. And anyway, we don't require this HL of full strength. We don't require that. And especially for the first two theorems. Sorry?
I have a question.
Sorry?
Whether T is missing in the second statement, like in the Lindelof hypothesis, like half plus IT is T per epsilon, right? Something you're using? Like T, the parameter T is like.
Yes, parameter T is there, but anyway, we are considering in terms of weight and level.
Okay, parameter is implicit or like it's uniformly bounded
Sorry?
in T. Whether it's uniformly bounded in T or like it's implicit there. T is implicit there, parameter.
Okay. So, and so it is known for all, the hypothesis HL is known for all L up to 8 by Gold-bach and Jacquet, Kim and Saidi and many others. It was known before. And the convexity bound says that we can take lambda to be 1/4 for all such this. And recently, Newton and Thorne, they proved that if the level n is square free, then this function, this is automorphic for all values of L. So assuming their result, so we can take lambda L to be at least 1/4 or less than equals to 1/4 for all values of L, and at least for square free level. Okay. This is Newton and Thorne. Newton, Thorne.
But it will be cuspidal, right? So it's always
Cuspidal. Okay. So we should go there. And up to L8 it was known before. Yes. And okay, so let me state our result here. The first theorem. So we have proved that we have considered intervals of that form first. So -2 to delta, where delta is positive. Okay. So for such an interval, we have find some, there exists a function theta to this strictly increasing such that there exists a prime p less q to the power qf to the power 2 lambda 1 by 1 plus theta of delta with lambda fp belongs to I. That means that interval. So note that this is delta is strictly positive. And here this lambda 1 is the, what corresponds to the hypothesis for sim 1f, which is nothing but f. It's fine.
So your A is 2 lambda 1.
Yes, 2 lambda 1 by 1 plus lambda. And at least in the weight aspect, you can consider lambda 1 to be 1/6 due to a work by Jutila and Motohashi. And the second statement, second result, the second theorem now we consider intervals of that form minus delta to delta, where delta is belongs to 1 to 2. This is half of n again. And so again, here we find some, it's better to write this to be theta 1 and theta 2. Such that there exists a prime P less QF to the power 4 lambda 2 by 1 plus theta 2 delta. Okay. Lambda FP is an I. Okay. So anyway, so I should also mention one particular thing. I mean, so these results, I mean, can be extended to some other intervals, but not all intervals. So I should just mention which kind of intervals for which such results can be proved. Is that let I be such that there exists some kappa positive and some natural number L, kappa L, and sequence of non-negative integers they are non-negative integers such that for all x in the complement of I, we have sum over BL times UL by UL of x by 2 is greater than equals to kappa. So here this UL is the Lth Chebyshev's polynomial.
What is the lambda 1 and lambda 2?
So there, I mean, there corresponds to the, I mean, this hypothesis. The exponent.
Lambda L.
Yes.
So lambda 1 is 1.
Yes, lambda 1 can be taken 1/4, and in fact, in K aspect, it can be taken 1/6. And with improvement for subconvexity bounds, one can improve these results also. So stop here.
Thank you, Ratnadeep, for this nice talk. Any question?
Yeah, thank you for the very interesting talk. So What in the last condition? What is the UL here?
Okay, UL is the
Chebyshev polynomial.
I've-
And where does it come from precisely?
I'm sorry.
I mean, where does the condition come from?
Actually, so the proof. Okay, so just give me 2 more minutes. Okay. So I give the sketch of the proof. So we can define a arithmetic function HFN, which is supported on the square free integers. It is, I mean, defined by some HFN by n to the s is product of primes 1 plus, I mean, given that condition, sum over BL lambda f p to the L 1 less than L less than L p to the s. So this L function can be written as a product of the symmetric power L functions. So a sums of this form HFN of some with some smooth waves, say 3x. So that so for this sum, we can have a upper bound by using this hypothesis, while this gives an upper bound by while this assumption gives lower bound. Lower bound is provided by this assumption. This we call this A. So now comparing these two bounds, we can get the contradiction.
Any other question?
You look at Vinakar's paper, I think at least in weight 2, or maybe if you have cuspidality up to 5th power, which probably was not covered by Shahidi, then all symmetric powers automatically cusp forms.
So that means, I mean,
Okay. But you have to check. I don't remember whether he did this only for weight 2 or general weight.
so that means, I mean, so this the result by Newton's ternary is not required in that case.
Yeah, but I don't know what is the point of not Newton. We must have explained because Vinakar had some paper where he should the crucial point was sim 5. If there is some assumption on the form F, then up to sim 5 is cuspidal, means all higher powers are covered. So that of course can't be covered, otherwise they would have put this theorem.
Yes.
But they prove that these are all Lagrange function is true for symmetric power. Is that content or they have something extra?
No, I don't think there is anything extra. I don't think there is anything extra.
No, because that's the main interest. But then their form F maybe Vinakar I think has some restrictions on the original.
Okay. That might be true.
Maybe weight 2 or something. But yeah, but it is there in this paper. Because he has been working on this for a long time.
So this arithmetic conductor, you mean analytic conductor only, right? That so the upper bound for this prime which you are capturing is in terms of analytic conductor of F power. This lambdas are actually the corresponding symmetric squares lambda L.
Yes.
I mean
So I mean, you can take all these to be 1/4 at least.
Sorry.
You can take all these lambda1, lambda2 be 1/4. I've just mentioned these two theorems. For this, I mean, in fact, everything is known.
This is L half plus IT of F only, right? Not symmetric square F, right? Symmetric LF, right?
I'm really sorry. It is, of course. Sorry. Of course, it should be. Thank you.
Does this have any impact on this sign changes problem?
Yes, but I don't have much time, but okay, I just can mention that. So what I've proved that there exists primes, which is of size an equal to be 1 plus epsilon, such that lambda 2 is less than. But for this your result, we don't require this kind of argument.
Both K
Yes.
and N vary?
Yes,
Oh, that's good.
but that doesn't require like that.
So if you,
I mean, the arguments we required for the first two theorems, it's different.
but if you get a square free n, from there you cannot get a p satisfying this. So the first sign change
No,
in
no.
terms of square free.
The point
is
is that, so these two results are, it's valid for certain intervals, which satisfies this kind of relations. Okay. So that's why we just, mentioned intervals of this form, so this and this. So we need to consider this -2 to 0 interval separately.
Yeah, so you need open.
Yes.
You have to put delta 0 actually. So that
Where?
you are getting lambda negative. You open it at 0. Those are the only
Yes.
possible negative values.
Yes, but
But that is, this is not covered there, but that may be easier actually, as you were saying.
yes,
This must be easier.
easier.
Yeah.
Any other question?
On P is sufficient to prove, yes, prove your result, this theorem 1 and theorem 2.
Which bound?
Your,
This one?
yeah,
No, it's completely different. It's another theorem.
okay. But there is
So-
a result like, in place of 1, there is a like 1/2 minus 1/4. This bound is not 1 plus epsilon.
No, we haven't addressed this question. We just address some intervals of particular interest.
Okay, in some interval.
Yes. While the result of Lemke, Olivier, and Horner is for all intervals. However, the constant is not that explicit. This.
Okay.
Yes, that can be calculated effectively. Which?
These exponents are they less than 1, or like what are like should
Of
the
course,
size?
look,
So
this theta1 is non-negative, okay, and
right.
this lambda1 is can take 1/4. So
And I think expected size should be just epsilon qf to the power epsilon. Expected size.
yes, of course.
We expect that.
In fact, that can be proved under the assumption of
Lindelof.
general Riemannian hypothesis for all symmetric powers.
Maybe Lindelof, I think.
Yes, that can be proved. Yes.
And what is happening around the interval 0? So the small interval, which is around 0. So, right.
So
So you are taking the interval which has length at least 2, or in the first theorem you are taking the interval which has the starting point -2. So the small interval around 0.
I mean, that doesn't satisfy this kind of.
Oh, so is it difficult case or something?
Yes, of course.
Okay.
As long as you go, I mean, take delta to be near 0, it will be more difficult.
Okay.
Condition in this second one. This your theta function, theta 2, yeah.
Yes.
So is it also strictly increasing?
Yes, strictly increasing. So, but if you require, I just, it's difficult to remember. I just put some, here this theta 1 is the value of theta 1
Yes, find
near
expression.
0 is 0, and at theta 1 at 1 is something like 0.3956. And similarly, for this one, theta 2, the limit is to 0, and theta 2, for example, at 3/2, here we are considering from 1 to 2 is 0.903, something like that.
Yeah, this just these general intervals that you're talking about. Here you get the like in that one you have lambda 1. Here you have lambda 2.
Yes.
Here you get the lambda in terms of these BL, something like that.
Yes.
Okay, and the theta will also depend on. So
Of course. Yes.
you're getting it kind of explicitly in the paper, or there's some dependence you're just saying?
No, in that paper, I mean, there is a generic theorem
Okay.
where we consider this case,
Yeah.
and these are two particular cases.
Okay. Okay. But in the proof, you can, I mean, if you're given the BLs, you can build it actually. Okay. That's nice.
Any other question? Yeah.
Yes.
0.4 something and limit is going to 0. So how is it in, it is a positive function also?
Of course. Yes.
Increasing. 0, 1.
Which one?
0 then. Okay. Any other question?
I just mentioned one more thing. It is not 1. Here the interval is from 1 to 2.
So if there is no further question, let us thank the speaker once again.